this is awesome. Thank you so much for being here, and thank you for staying for my presentation. I come all the way from Minnesota, and then everybody goes for break for coffee. It is not good. So I'm very happy that you are here. So he kind of told you who I am and where I'm coming from. And so I'm going to try to give you some ideas of our work that we did on complexity analysis and network liability of complex networks. Of course, whenever we give talks, besides the graduate students, they tell you what they know, what they have found out. When I give presentation, assume I know nothing. And when I give presentation, I'm always looking for more ideas. I'm always looking for more feedback. So if you hear something today and you see that you have an idea that you can, we can work together, I'm always ready to go for it. And I have no tiredness. Whatever area you are working on, and if this excites me and if it has to do with mathematics, then you can have me on board. Okay, that's the kind of person I am. Okay, so we are going to move on. So first, always I say where I am from. Okay, so this is where the Morocco is, right there. And I'm coming from here, which is United States of America. And all the way from there. And, oops, sorry, I have to figure it out how this works. Okay, there. Okay, so now we have United States, and I am from Winona, that is in Minnesota. And this is the state of Minnesota that he said. And these are the pictures of my campus. In Morocco, you have flowers all the time. And so you don't pay attention. I see a rose blooming. I'm like standing there and taking pictures. I see a hibiscus blooming. I'm standing there and taking pictures. Because in Minnesota, I get this most of the year. And I get this in fall, like from August, September, just a couple of months. And then I get spring, I get spring when I get all the flowers. That's again for a couple of months. And then I get summer. That's again for a couple of months. I mean, not even a couple of months, maybe a month and a half. So right now, the snow is probably melting and people are planting flowers and things like that. But most of the time, it's kind of like this, all the time. And so when you have all covered, you don't recognize people because people are all covered. And so then when snow melts, then you find people. Yes, this is what it is. So this is my campus now. See, you can see it is in spring. Okay, so here is the Mississippi River. If you look at United States map, Mississippi River goes from the top to the bottom, and we live in the top. That is Mississippi River. And the state of Minnesota is known for a state of 10,000 lakes. 10,000 lakes. So there are lots of lakes. And this is one of the lake. And this lake is about 3.5 miles. And there is another lake over there, which is a mile and a half. And so my best recreation and doing problem in my head is to walk or run in these two lakes. That's about 5 miles. Okay, moving on. This is just inside the campus. This is how it looks like. But you see there is no flowers, no branches, nothing on these trees. This is how they look most of the time. But anyway, that's my campus, and I'm from there. This is again inside the campus. This is actually the administrative building. But the thing about the campus in my campus is you cannot have cars and goes through inside. So the whole campus is kind of surrounded and the cars kind of go outside, not through the campus. So that's kind of the best thing in the campus. See, here I see the campus are more like buildings, and you cross the street and then you go to another building. It's kind of not like that. Some campuses are like that. Okay, so now you know where I'm from. And I'm going to start presenting something. Now, all the talks that I heard so far, I see a whole lot of writings and I don't see enough mathematics. I'm a mathematician. Now, even if you make a drone or if you're making a model, there must be some mathematics working. Otherwise, how electricity is flowing or how any mechanical object is moving, it's not possible. My son does PhD, he's working on PhD on biomedical engineering. And even though he's working on robotic arm and everything, he has to explain to me what mathematics is he working on? What is the mathematics that doing all this job? Not just data, data, data. There must be something going on. So I'm going to give you some mathematics. And if you think that you need a math person for your research, I'm here, okay? All right, so I need to acknowledge these people in my life. Sorry, oh, these kids are moving back and forth. Oh, no, how am I going to go? There. I want to acknowledge these people in my life. We three of us here, we are at the university. You guys are late, come on. -5. Say that again? Oh, don't fall. You'll have to take me to emergency. Okay, so these are the people that I want to acknowledge. One of this person is sitting right there, okay, and her name is Dunia Lotfi, and I don't have a picture of Professor Moraki. But this is what we work and we pound on things and we do things. Sometimes she tells me you don't understand and I tell her you don't understand, and then we kind of work overnight, or we want to work on Skype or Facebook messaging because I am trying to explain the mathematics and she's trying how things work. So it's kind of a very good experience on this. Okay, let's go on. So this is abstract, don't worry about that. Now, these are the papers. So when I was going to do this keynote presentation, I thought what I want to talk about. Okay, I can just come here and tell you stories, or I can tell you things that we have established and published and are also already presented at different conferences. So these are the 3 papers, actually 4 papers, that I'm kind of doing a synopsis for you and will tell you what we are working on. And we also have more that we are working on, and maybe some other time or maybe next year you will hear what we are working next. Okay, so moving on. I told you at the very beginning that we are going to talk about complex network, and this really, really intrigued me. I look at that not just something that I need to work on, but I look at that because I find that it has an enormous amount of information. Just think about, President Trump tweeting, and just think about the network that it's going through, and you see how many, if you just put Trump in one node, think about the degree of that node. It's amazing, right? And all that information just kind of excites me. And I do a lot of graph theory and find the properties of the graph that we have. So anyway, moving on this one. So here we are talking about different kind of network. Okay, social networks belong to all of this. I use WhatsApp quite a bit. I think they use WeChat in China, and for some reason, Chinese government doesn't allow any other social network. But anyway, these are the ones that I thought is intriguing. And this is technological networks, which can be electrical, internet, transportation, that kind of thing. This biological network is exciting because my son works on biological network. How our brain is, connected to different parts of our bodies, and how it is connected through our spine, and how all this neurological connection, because his research is making the prosthetic arm and limb feel real. So when he finishes, or his group of people finishes, anybody with the prosthetic arm can feel that this is hard, this is soft. And it's just amazing how this biological neural network works. But anyway, so moving on. So about this multimedia, it also intrigues me. I haven't gotten a whole lot of things with it yet, but it's in my radar. I want to know more. You can see that there we go. It was constantly changing. We not only want to know how the network is complex, but we also want to know how multimedia can help us understand that, and what is the security in it, how each network connect to another network. So those are also the other important things that I'm very, very interested in, particularly planning, design, and implementation, and developing them and testing that network is really a secured network. Okay, moving on. So what are the different types of networks available? When I look at it, you know, in mathematics, if you give me a set of data and you tell me, here is the data that's happening for last 5 years, and you ask me, can you predict what's happening, what will happen next 5 years? What do? I fit some kind of polynomial or some kind of graphing or some kind of function, right? And I can predict, okay, if this polynomial fits this, and this polynomial appears to move like this or move like this, I can say, okay, your economy is going to down, or the profit is going to go up, or the cost is going to move this way, anything. But I'm still thinking, if there is a random network, I close my eyes and you say, Joyati, here is a network. Now, can I take that network and can I fit it in some of the other networks that I already know? If I can do that, then I can get a whole lot of information from the network that you gave me, and I can predict what is going to happen. So those are some of the things excites me. Now here, the three well-known networks that uses degree distributions, if I will explain what degree distribution is, and we talk about scale-free networks, small world network, and random networks, and it all has to happen with nodes and edges, and the degree of the nodes, and also how the edges are connected. Okay, moving on. So how does the degree distribution work? So what do we do? I cannot control this. It's going faster than me. There you go. Okay, so how does the degree distribution work? Given a network or some kind of graph, for example, I have here 10 nodes. And if you look at each node, well, this node has degree 1, this node has degree 3, okay, so on and so forth. So this node has 1, 2, 3, 4, 5. So what is the degree distribution? I try to find how many nodes are there, say with degree 1. So if I'm finding how many, so here is one node with degree 1, here is one node with degree 1, here is one node with degree 1, here is one node with degree 1. So there are 4 nodes of degree 1. Now, how many nodes are there altogether? There are 10 nodes altogether. So what is the degree distribution? That of 1 is 4 over 10. And so this is how we do degree distribution. Now, there are many such distribution that we use, probability distribution, Poisson distribution, and each one of this is little differently planned than the other. So here is a scale-free network. I'm going to give you the ideas of the scale-free network, and I will go deep into what we actually worked on. So here is a scale-free network. What does this network has specialties? This network have hubs. Okay, so if you say, for example, the flights, the delta, they have hubs. So that means that from that hub, that node, it has more degree, higher degree. So these are called, there are nodes with high degrees. And this high degree indicates that more nodes are connected to this node. It's probably clear. It also uses, this is called power law degree distribution. It's another expression that we use for the power law. It has something to do with the power of how many nodes it is connected to. Okay, moving on. Next. Okay, this is small world network. What is the specialty in this network? It uses a general binomial distribution. Like I said, this has different kind of distribution, and these, for example, neural networks in the brain. I absolutely love this. It's amazing how our brain works. Even though we are all human beings, but somehow something is different inside our brain. And it's amazing how this works. And then you have the distance between any pairs of nodes is relatively small. So we use clustering. And this kind of small world network, the clustering, that means if I am connected to you, you are connected to him, then he is connected to me. That's called transitivity. You know, that transitivity is high, and we try to add more clustering connected nodes and to see what is happening if this, how it gets bigger. So the popular term we use, we call 6 degrees separation, and this is how this can be described, and this uses some method called generalized distribution. Okay, moving on. Now it is the random network. So what does random network do? It uses Poisson distribution, and these Erdo-Renai models are very useful to use this, and they are very high dimensional, very high dimensional, and edges treated as random variables. Sometimes it's not just only the nodes, but edges are also becomes important for us to study the network, and it uses Poisson distribution. Okay, moving on. So now, after I gave you the story of complex network, I explained different features of complex network. I explained the different interests. It's kind of like you are with me in a journey, right? I mean, you are now going a little bit deeper and see more things. So what do we mean by the complexity of a complex network? Just by the name complex network tells me there must be some kind of complexity. It is not trivial. So what does the studying complexity means? It means that we analyze the structures of the network. We try to work on network that is really meaningful to our real world situation. We try to understand the properties, okay, what is happening, okay, and if we know what is happening, maybe from the history of what's happening, we can predict what will be happening next. So you can see this is a very broad area. Now to work on something, so you have to publish paper. You can study all your life long, but if you don't have some result, you are stuck. So you have to concentrate and focus on something that you can work on. And so we decided that we want to focus on these two families of complex network and see if we can collect their robustness. And then we will have some result, and then we can publish something, right? Okay, so what is the meaning of robustness of a network? So we try to, this is the ability to withstand failures and perturbations. If there is any disturbance happening, will it be stable? Will it be secured? We want to adapt any random changes. Can it stand any random changes? Something happened to someone, can it still continue whatever this network is doing for us? The capacity to tolerate changes. So over the time, if there will be changes happening, can it still be steady? So these are the things that we want to say when we say robustness of a network. Okay, so now, come with me, and I'm now going to go in more detail into the research, okay? I'm warning you, there will be some mathematics. If you love mathematics, stay with me. So what do? We suggest a structural characterization of robustness using the spanning tree in a very easier terms. That way a student can connect. More big terms you use, it kind of gets lost. So what is this? It is a measure. It's a quantitative measure. It's something that I can connect to. It's some kind of number. It's a measure of the number of spanning trees to evaluate the robustness of the network. What does robust do? Most robust network is a network that will have the highest spanning tree entropy. And how do we define it? We find the entropy by logarithm. Okay, this tells you the number of vertices, okay, of the graph as goes to infinity, and this is the natural logarithm of the tau. What is tau? Tau is the number of spanning trees and divided by the number of vertices. So now you can imagine the vertices are becoming infinity, more and more vertices. Okay, so what is the general method? Is the traditional method. Okay, this is very, very known to everyone. If you are taking any graduate level course, you already know Kirchhoff's matrix tree theorem, right? So what is the Kirchhoff matrix tree theorem? You try to compute the complexity of a graph by tau g or tg is here, which is -1 to the power I plus j, okay, determinant of this. Well, what is this? This is a matrix. Okay, first of all, think about this. What is this? So LG, this is a Laplacian matrix. This is a matrix that is a difference of the degree matrix and the adjacency matrix of the graph. Now you take that matrix, you take away one column, one row and one column, and then you find the determinant. Depending on which one you are taking, it will be positive or it will be negative, and then you find how you get that. Okay, so this is the formula right there. Okay, now what happens if I have a network which is huge, which is big? This is impossible. This becomes very, very complicated. So we need to have some kind of solution for it. So here is the limitations of that Kirchhoff theorem. Okay, it is not practical when to use for the large and complex network. So we need to find some ways to do it. What did we do? We suggested that we want to use a combinatorial method. Something about cutting and adding and counting, maybe that can help. But I cannot do this for a large one. But I can start doing some kind of iterative process. If I can say, okay, this works for 3, this works for 4, this works for 5. What can it work if I have that number of vertices going to infinity? Can I have a grasp of that? I hope everybody is getting it, right? I'm trying to make it as simple as possible. Even if you are not in this topic, after my talk, when you leave, you will have some idea, all right? Okay, that's the goal. Okay, so this is the solution we mentioned. We were going to talk about 3 combinatorial methods, and we give them a name. We called it reduction and bipartition, okay, and a decomposition. And I will explain a little bit how these methods are working, and then I'll show you the result. So what does reduction and bipartition method? So this is like it approaches to construct two scale free networks. And then we are going to look at the flower network and mosaic network, and then we will try to find their complexity. How are we going to do the decomposition method? We are going to calculate the complexity of 2 small world network, and we are going to choose exponential small network and the Koch network. Okay? All right, moving on. So here is that approach. So how are this reduction approach is going to work? So I'm going to show you the picture. So here I started with this graph and I add more edge to it. So this is the second stage, this is the third stage. So this is a 3 reduced graph. Okay, so as we move on, so we look at what are the property when I go for kth. So I showed you first, second, third iteration. Now I'm on the kth iteration. Number of vertices will be the vertices starting here, and the number of edges are going to change, number of faces are going to change. Now the average degree is going to be like this, and the complexity will be like this. So the idea is to use this approach to find the complexity with a large number of edges and see how it works. So we started working on that. Let's look at what is the bipartition approach. Now, I explained to you what is the reduction approach. Now I'm going to explain it to bipartition approach. And before working with each one, and each one was becoming complicated, we said, why cannot we do this first and this next? And I will come to that in a bit. So what is bipartition approach? Bipartition approach is to just throw in more nodes in there. So in this, I threw in another node, another node, another node. Now this is the second stage, this is the third stage. So now because if I and you are friends, between two of us, we meet somebody today, there is another node in there. So this is how the network, any kind of social network increases, right? It just uses bipartition method. Okay, so then these are the formulas that we're going to use. You don't have to memorize any of this formula. Just remember that I showed you, okay? And then we are going to move on. Again, this is our goal, right? To simplify the calculation. So now what did we do? Now I'm going to show you some results. So now in here you can see we are combining both approaches. So not only say I am one node and he's another node, and we meet somebody today. So now this person is becoming node in here, but now I introduce him to him. So not only now he is a node between us, but then there's an edge between him and there's an edge between me and him. So not only the nodes are increasing, the connection, the edges are also increasing, right? So the combining both approach makes sense, right? Okay, so combine both approach, and so here two people, okay, we meet people. So this is the second iteration, first iteration, this is the second one, and this gives rise to a two-flower network, okay, all right, which is something we can handle. Okay, moving on. Now, when we look at the topological properties of two-flower network, and I showed you how the formula worked in each way, and then we figured, oh, if we move on to n, all I need to do is this. Now, this requires a whole lot of mathematics, mathematical induction, counting, all kinds of those proofs. This is what happens for that. This is what happens for this. I think something might be missing here. Okay. All right. Number of faces, degrees, and this is the complexity. Something must be missing here. Okay. All right. Moving on. This is k-flower network. So now we have generalized it, right? So not only we have one, but now we can use two, but maybe there are three more people, maybe three, or maybe there are four. So see how this network is growing and growing. Okay, this is now three-flower network. And then we found out, yes, this is what the results are for the k-flower network. Again, you don't have to memorize this. You don't have to see that this there. But then I will show you the analysis, and you will probably have a better idea what I'm talking about. Now, this is a mosaic network. Now, this is a particular case of our understanding of our bipartition and reduction method. And just nice picture, very, very nicely drawn by one of our author. And then we also say, okay, let's figure out how this is working. What are the topological properties of this network when we add more and more nodes and more edges? So this is what we figured. This is k-Mosaic network. Now we have generalized it. So there might be k edges and more nodes, and then this can continue. And finally, we find out that this is probably the best possible calculations that we can make on the k-Mosaic network. Okay, all right, so we got that far. Next, what we need to analyze, right? What are we doing with all the results? So we find out that k-flower network and k-Mosaic network has the same complexity in our results. And we find out that the combination of this method lead to the same complexity, which is kind of nice that we can, if we learn one, we can have the idea about the other. And then we, even with the difference, right? the spanning tree's entropy follows this rule, and this one follows that rule. So that's kind of nice that we have a grasp on the spanning tree entropy, which gives the complexity of the network. Okay, moving on. When we try to look at it in a picture, the pictures speak a whole lot of things to us, right? So as we increase the number of k's, and the entropy, look how the spanning tree entropy of the k network is here, and how the spanning tree entropy of the k flower network moves. So now we have an idea that how things changes, okay, by each one. Okay, now. Once we study these, I told you the ideas with using the network, that's kind of easy to understand. But then we want to compare and see if we have the same average degree, how does the rho entropy changes or behaves. So this is what we tried. We used Koch network, we tried Hanoi network, and the average degree is this, and we find out what the numbers are, and then we realize that as an average spanning tree, okay, compared to that, okay, same average degree, and we find out that 2-flower network, okay, is more robust than the other networks using this process. Okay, so I told you about the reduction bipartition, and I told you how the analysis is done. I showed you some formulas and stuff, and let's move on to see what is. Okay, so I forgot about that. This is the comparison of the mosaic network, and 2 mosaic network. This is average of 4, and this looks like the most robust in other networks with the same degree. So that's kind of nice. Okay, now moving on. Decomposition method. So decomposition method is you can think about decomposition method as divide and compare and conquer. So what are we doing? We decompose the original graph into subgraphs. We compute the spanning tree, and then we try to obtain the complexity of the original graph that we started with. And we split it like this. This is like a kind of a cross product kind of thing. Okay, so here is a star and chain network, and you can see how the picture splits and how the product of the complexity, entropy, sorry. Okay, so we in our different papers that I told you, we discussed 2 types of small network. We used exponential small network, small world network, kind of grows like this by iteration, and we use Koch network, and it grows like this. Using these ideas, we looked for the topological property. Using the spanning tree entropy. These are our mathematical results. These are hours and hours and hours of work, okay, probably months of work. The graduate student needs a PhD, right? Okay, so then finally we want to compare and see how they behave. Average degree is still the same. Koch network and exponential small network, they have the same spanning tree entropy. Okay, moving on. What did we actually then found out, and where we are heading from here? So all the applications that we did, we are always looking for any kind of network, like I said to you before. If we can fit a network or a sub-network in any of the networks that are known, then a lot of things we can understand, and we can move on from there, and we have a better idea about how things are happening. We have to use entropy of spanning tree. I'm sure there are many different ways the robustness of the complexity can be measured, but we used spanning tree entropy. This measure gives us an idea of the resistance of a network over a longer period of time, like n goes to infinity. So we calculated and compared spanning tree entropy of different complex networks and with the average degree, and we find what the robustness stand. And this is something we are working on right now. We are trying to analyze other types of complex random networks. These are very, very exciting network, and we want to find out how the complexity of these networks behave and works. Okay, finally, thank you for being here, and I'm done.